live in a large and interesting universe, but how did it get here? The current best explanation for the origin of the universe is the Big Bang Theory. This series of videos aims to describe the Big Bang Theory in detail, starting with the history of the most relevant experiments and an explanation of related scientific concepts. Before we get started talking about the formation of the Big Bang Theory, we should first discuss some very important and relevant topics. First, let's talk about light. Light is interesting because it behaves like both a particle and a wave. For right now, let's think of light as a wave. All waves are characterized by a wavelength and a frequency. The wavelength is the distance between each peak of each cycle of the wave, while the frequency is the number of peaks that pass any given point every second. Wavelength and frequency are inversely proportional, meaning that longer wavelengths will have shorter frequencies and vice versa. Now, light is just a type of electromagnetic radiation, much like radio waves, X-rays, etc. We just happen to be able to see the electromagnetic waves that visible light has. For the curious, visible light spans the wavelengths from 400 nanometers for violet all the way to 700 nanometers for red, with orange, yellow, green, and blue falling in between. Now that we understand a little more about light, we can talk about a phenomenon known as the Doppler effect. Like light, sound is also a wave, just not an electromagnetic wave. I'm sure you've all heard this sound from a passing car. Notice how the sound changes as the car passes by. This is the Doppler effect in action. If the source of a wave is moving, then the peaks of its wave get bunched together in front of the wave source. If the wave peaks are bunched together, then their frequency increases. If the wave peaks are spread further apart, which is what would happen behind the wave source, then the frequency is lower. In the case of a sound, we hear a higher pitch at higher frequency and a lower pitch at a lower frequency. In the case of light, we use the term redshift and blueshift to describe an observed change in the frequency of the wave of light. These terms just mean that the observed light has a shorter wavelength, which would be shifted toward the color blue, or the light has a longer wavelength and is shifted toward the color red. These changes would be observed if a source of light were moving toward or away from you. Since ancient times, man has sought for an explanation for the existence of the cosmos. Many of these ideas were nothing more than stories told to explain the unknown. It wasn't until the early 20th century that ideas leading toward the Big Bang Theory were formulated. At this time, astronomers were studying the heavenly bodies using a variety of methods. As you can imagine, getting data like the distance to a celestial body, such as a star, would be quite difficult. This distance can be measured using a technique known as parallax. This is done first by measuring the angle of a star on the sky with respect to the Earth. Then, 6 months later, we measure the angle of the star again. Since we know the diameter of the Earth's orbit, we can measure the distance of the star using simple trigonometry. Astronomers also looked at what celestial bodies were made up of. When different chemical elements release energy in the form of light, we can identify what element it is by a characteristic pattern of wavelengths that are unique to every element. This process is known as spectroscopy. So, how does all of this get us to the idea of the Big Bang? In 1929, Edwin Hubble was studying the stars of distant galaxies when he noticed something odd. While studying the chemical makeup of these stars using spectroscopy, he noticed that the pattern of wavelengths for these stars did not match those of any element or combination of elements. He eventually identified the spectra of these stars as corresponding to hydrogen, from which the light had been redshifted. Hubble then showed that the amount of redshift was proportional to the distance that the celestial body was away from us. The obvious conclusion from this data is that these redshifted heavenly bodies were receding from the Earth and each other. These observations are described as Hubble's law. Now let's jump forward to the late 1940s. In 1948, physicist George Gamow deduced that if galaxies are flying apart, then the entire universe must have been concentrated in a single point at some time in the past. Another scientist, Fred Hoyle, ridiculed this idea and named this idea the Big Bang Theory, as some sort of joke. Surprisingly enough, the name caught on and has described this idea since. Gamow continued his work, which later predicted that there would be a leftover radiation signature from this Big Bang that may be detectable. He proposed that when the initial expansion of the universe happened, that the light released from the hot, dense state of the universe would continue to propagate and eventually shift in wavelength as it lost energy. It wasn't until the 1960s that we actually found this proposed background radiation, and a wonderful mistake. Two men, Arno Penzias and Robert Wilson, were working at AT&T Bell Laboratories trying to reduce some noise on a satellite communication system. There was a faint crackle that was added to phone calls that were using the system, and they were tasked at finding what was causing the problem. These men considered a myriad of possibilities, including reduction of bird droppings on their satellite equipment, but were unsuccessful. One thing that they did notice was that the noise appeared at all times of the day and at all different positions of their antenna. After consulting with some astrophysicists at Princeton, they realized that they had just discovered the cosmic background radiation left over from the Big Bang. Both of these men would go on to win the Nobel Prize for this discovery. This discovery is what rocketed the idea of the Big Bang to being the most widely accepted scientific theory for the start of the universe. Many years had passed with predictions being made based on this theory, followed by empirical evidence that confirmed it. There was one main problem with Penzias and Wilson's discovery. The radiation that they observed was very uniform, which seemed to indicate that the early universe was filled with particles that were evenly distributed throughout. This is a problem because particles would not clump together to form stars and other celestial bodies if they were completely evenly spaced. This would mean that stars, planets, let alone life, would not exist, and this is clearly not true. Turns out that we just needed more precise data. In the 1990s and the early 21st century, there were two projects that broadened our understanding of the cosmic background radiation. These projects are known as COBE and WMAP. The COBE satellite took more precise measurements of the background radiation, which were followed by even more precise measurements by the WMAP project. The results of these projects show that the early universe actually was not uniformly filled with matter. The possible clumping that was observed seems to give even more evidence in favor of the Big Bang.